In Part 7 of the Unit 3 notes, we will be discussing the mole and molar mass conversions. The mole, or MOL, is the SI base unit used to measure the amount of a substance. It is defined as the number of carbon atoms in 12 grams of carbon-12. A mole is such a large quantity of atoms that it allows the atomic mass of an element to be measured in grams. So this is something really useful because it can allow us to bring things from the scale of atoms up to the macro scale, something that we can actually touch and manipulate. The number of particles in a mole has been determined to be 6.022 times 10 to the 23rd by Amedeo Avogadro in 1811. This is a number that we will be using a lot in this class. A molar mass is the mass of 1 mole of a pure substance. A pure substance can be an element or a compound. The molar mass of a substance is numerically equivalent to the average atomic mass found on the periodic table. The only difference is that you must round to 2 places after the decimal. So for example, if you were asked for the molar mass of lithium, you would look at the symbol on the periodic table and you would round that mass to 6.94 grams per mole. If you were asked for the molar mass of carbon dioxide, which is CO2, you would take the mass of a single carbon and then 2 oxygens, and you would add that together. And that would be 44.01 grams per mole. Mass and moles can be converted using an equivalency. 1 mole is equal to the molar mass, along with dimensional analysis. The molar mass of the conversion factor will always be the atomic mass found on the periodic table rounded to 2 digits after the decimal. The mole of the conversion will always be equal to 1. You should round the final answer based on significant figures rules. So here we have an example which is already solved. A chemist produces 11.9 grams of aluminum from a chemical reaction. How many moles were produced? Since we are starting with grams, grams is going on to the bottom of the conversion factor, so that's the dimensional analysis part. So we're canceling out these units on our way to a new unit of mole. Once we have established which unit goes on the top and which unit goes in the bottom, we can fill in the numbers. Mole is always equal to 1. Grams we get from the periodic table based on the element or compound. Aluminum has a molar mass of 26.98. From here, we are going to multiply the top, so we're multiplying by 1, and then we are dividing the bottom, dividing by 26.98. So that leaves us with 0.441 moles of aluminum. Now when you're rounding for significant figures, these values are not going to factor in to your final rounding because these are not measured values. So you should be going based on your mass or mole value from the beginning. So this had 3 significant figures. We're multiplying, so we're counting total sig figs. Our final answer has 3 significant figures. The 0 out in front is simply a placeholder. For our checkpoint, we are going to be going through 2 mass to mole and mole to mass conversions. Whenever you're doing these, the first thing you should do is write down the number with the unit that you're given. So we're starting off with 5.10 moles of boron. Whatever unit you start with has to go on the bottom, and you should include the element or compound along with this. We are asked to find grams, so grams of boron is going to go on top. Moles is always equal to 1, and mass you get from the periodic table, and you round to 2 places after the decimal, so 10.81. We are multiplying the top and dividing the bottom. So this is going to come out to 55.1. And that's grams of boron. For our second problem, we are starting with 20.3 grams of elemental oxygen, which is O2. Oxygen is a special type of element, which we call a diatomic. These are elements that never like to be by themselves, so if they don't have anything else to bond to, they'll bond to a like atom, so there'll be 2 of them. And this is going to be important for our calculation. We are trying to convert from grams of O2 to moles of O2. Moles is always 1, and grams is from the periodic table, but this time there are 2 oxygens. So my mass of 16.00 is going to get doubled. So 32.00. From here we are going to multiply by 1 and divide by 32. So that gives us a mole value of 0.634 moles of O2. That concludes part 7 of the Unit 3 notes. When we come back for part 8, we will be wrapping things up with Avogadro conversions and two-step conversions.